This next video is going to build on that idea of symmetry to use the test for symmetry to determine if a function is even or odd. Now, I struggle with this one a little bit because we are going to later talk about graphs being odd or even, and we're just going to determine if they're odd or even based on the leading term. So for example, if you look at this guy, the leading term is 2x cubed. So a leading term is the term with the highest degree on the exponent. And so since this highest degree is a 3, we're going to call it odd. We're not going to say even, odd, or neither. We're just going to call it odd. This one too, the leading term, it's a degree of 3, it's odd. This one, the leading term, has a degree of 2, it's even, right? So we are going to determine whether it's even or odd based on the leading term. But this is different. This is talking about using symmetry to determine if a graph is even, odd, or neither. So let's say we didn't know, I don't know why we wouldn't know the leading term because we're looking at it, but let's say we just wanted to see if it has even or odd behavior, and if it doesn't, we'll say neither, even though something can still be odd and not have this. It's a very specific feature of an odd graph and an even graph that we'll talk about. So that's my disclaimer, but let's do it. So an odd function, if we take any base odd function, so a base odd function is something with a leading term with an exponent of 1 or an exponent of 3 or an exponent of 5, okay? But 1 and 3 are the two graphs we know. And if we look at their graphs, I'm just going to move this guy over. So if we look at the graphs of these odd functions, so y equals x is a line, it passes through the origin, and it looks like this. Y equals x cubed also passes through the origin. Whoop, that's a bit off. There we go. And looks like this. If I asked you what type of symmetry do these two base odd graphs have, hopefully you would notice that they're symmetric about the origin, because they have something down here in the third quadrant, something up here in the fourth quadrant, or first quadrant. So even if I did negative x, another sort of basic odd graph, it's going to start up here and go down. Oops, sorry, that's the cubic. It's going to go like this. It still has that origin symmetry. Y equals x cubed, right? If I put in 0, 0, if I put in 1, I get 1. If I put in 2, I get 8. This is the graph, the shape I get. If I put in negative x cubed, it would be the same. It would just look like this. And in fact, every base odd graph has the same feature. So even if I did x to the 5, it actually still just looks like this. It just gets steeper quicker, okay? But all base odd graphs are symmetric about the origin. To test for origin symmetry, you replace x with negative x and y with negative y, right? We already did this. Even functions. Let's look at our basic even function that we know. Y equals x squared, right? That's our parabolic shape that looks like this. Now, this is not symmetric about the origin. This is symmetric about the y-axis. So every base, so even if I did y equals x to the 4, which again, oh, there's those y's and 4's, I can't write them. Y equals x to the 4. The only difference is that it would get steeper. So it would just be like skinnier or narrower. Okay, but no matter what, it looks like this. So even if I put a negative up front and opens down, it always has symmetry about the y-axis. So to test for y-axis symmetry, we replace x with negative x. Now, if a graph is neither symmetric with respect to the y-axis or the origin at this point, we will just say neither. Now, here's a little question. Why can a graph not be symmetric about the x-axis? How come we're not using x-axis symmetry to talk about a function? Well, if I draw something that's symmetric about the x-axis, what do you notice? What does it fail? It fails the vertical line test. It's not a function. So something that has x-axis symmetry is not a function, and so it's not going to be even or odd, and it's not even going to be in a function, so we can't talk about it. All right, so let's move on to the test. So what we're going to do is we're going to use a little bit of logic, and we're going to use the test. So what I mean by logic is that this graph can't be even. Because the highest exponent is a 3, it can't be even. So the only thing I would test for is if it's odd. Right? You can test if it's even if you want. Like you can go through and be like, oh, does it have y-axis symmetry? But I guarantee the answer is no, right? So what we're going to do is cut down on the work by saying, hey, what's the leading term? Since the leading term has a degree of 3, it only could be odd. Now, this is still going to be an odd graph, even if it doesn't have origin symmetry, but it's not going to be your basic odd graph. Okay. So to test for whether a function is odd, we would test for origin symmetry. Origin symmetry. In other words, we're going to replace x with negative x, we're going to replace y with negative y, and see if we get an equivalent expression. So this is y, right? So I'm going to go negative y equals 2 times negative x all cubed minus 4 times negative x, and then I'm going to simplify. I end up with negative y equals, since this is negative x cubed, it's going to stay negative, so we're going to write it as negative 2x cubed, and then a negative times a negative is a positive. And then to compare it, I have to make it y equals again. So I'm going to divide everything by negative 1, or multiply everything by negative 1, and I get y equals 2x cubed minus 4x. Is this equation equivalent to this equation? Yes. So it is odd. And if you are odd, you can't be even. So once I tested for odd and I found it was odd, there would be no point of testing it as an even. And now again, I could have looked at this graph and realized that it is odd from its symmetry point of view, because you have a point here, you have a point down here, you have a point down here that would also exist up here, and so on. Okay, so try this one. Again, you're going to test whether it's odd because the leading term is odd. So I wouldn't even test if it's even. Now, if you don't trust me, feel free to do all the tests. You could just be like, hey, is it odd? I don't know. Is it even? I don't know. And test and make sure if it's one of the either, or if it's not, you say neither. Okay, so give this one a test for odd. So check your origin symmetry. So hopefully you pause the video. We're going to replace x with negative x and y with negative y. So again, f of x is y, so we're going to replace that with a negative y. And then we're going to replace all the x's with negative x's. Whew, just squeezed it in there. And that 4, man, drives me bonkers. Okay. There we go. All right, now we simplify. We get negative y equals negative x cubed is negative, so we get negative 2x cubed. Negative x squared is positive, so we get minus 3x squared. Negative 4 times negative x is positive 4x. And then plus 4. Then I want to make it y equals, so I'm going to divide everything by negative 1. And I get y equals positive 2x cubed plus 3x squared minus 4x minus 4. Now, is this equation equivalent to this one? Heck no, right? 2x cubed is the same, but it's all of a sudden I go plus 3x squared. And I only have to fail one thing for it not to be equivalent. So this one is going to be neither. Now, if you don't trust me and you want to test if it's even, go ahead, but I guarantee it will never come out as even if there's the potential for it to be odd. All right, so let's move on to this guy. So this is one of those ones that I'm going to test to see if it's even, because my highest exponent is a 2. You can test if it's odd if you want, but it'll fail every single time. But I'm going to test if it's even. So to be even, you want to think of your basic y equals x squared graph, right? So if I was doing a test, I couldn't look in my notes. An even graph, I have to picture my base even graph, which is my y equals x squared. My y equals x squared has y-axis symmetry. So to test if it has y-axis symmetry, I replace x with negative x, right? Confusing, right? A point over here, same y value, opposite x value. So I'm going to replace the x with a negative x. So everywhere there's an x, I'm going to put a negative x. And then I'm going to simplify. I get y equals negative x squared is positive, so I get negative 3x squared plus 4. They are equivalent, so this guy is even. And because it's even, I don't have to test if it's odd, and so on and so forth. Okay, what about this last guy? Well, this one, I don't know, should I test even or odd? I mean, which one's my leading term? An absolute value of x doesn't really have an exponent per se, maybe a 1, but let's just test, okay? So if you're not sure what the leading term is, or you're not sure if you should test even or odd, just test both. So let's do the first. Let's test to see if it's even. So even is you replace x with negative x because it's y-axis symmetry. So we get y equals the absolute value of negative x plus negative x. The absolute value of negative x, no matter what, will be x, right? It'll come out positive, so we can still keep those signs there to make it look the same. Minus x, not equivalent. So nope. Then we test odd. Odd, we replace x with negative x, and we replace y with negative y. So we would go negative y equals absolute value of negative x plus negative x, and then we simplify. And then simplifying this, I simplify the x's first. So I'm going to keep it as negative y. Again, no matter what I do in here, it's going to come out positive. So I'm just going to keep that as absolute value of x because I want it to have the same, I don't know why I scroll down, same format as the question, and then minus x. And then I would divide everything by negative 1. I get y equals negative the absolute value of x plus x. And this is not equivalent. So it is not odd. So I'm going to say that this graph is neither. All right, so your quick check is here. Good luck.